It has to be normalized. And I said that thinking a little bit in the simplest possible system, which is a two-level system, a system in which you have one particle that can be either in state A or state B, and state A and B have different energies, we can get a little bit of a glimpse of what happens here. But just to remind you what I showed last time, when I say that if you have the probability of the system being in A, measuring my system in state A over the probability of measuring in state B will be e to the minus, this is e to the minus A sub A, e to the minus EA minus EB over KT. Right? So at least this, because the concept of normalization will cancel, this tells you the relative probability of measuring my system upon looking at my system being in state A or B. I pointed out that the only thing that matters for that probability is the energy of the state. If I have another state with the same energy, it will be as likely because then this is 0 and e to the 0 is 1. But this allows me to get a feeling also of what is the effect of temperature in thermodynamic systems. Because you see, if you look here, and you will see it very clearly once I develop the two-level system, you see that if the temperature is a very big one, so if what we call a very hot system, this number will be small, and we'll make it precise, meaning that KT is much bigger than EA minus EB. In that case, this number is close to 1. So what you are saying that the system is as likely to be in state A as in state B. So high temperature is another way of saying that the system is very likely to be in different states no matter what their energy is. Low temperature, on the contrary, makes this number very big. So this probability this ratio becomes very small, and the chances of measuring the system in state A, if state A is lower than state B, are very small. So when you have low temperature, what it means is that it's very unlikely that your system will be in a state that is above the fundamental state of the system. And you will see that that is a typical characteristic. Low temperature is associated with systems going to their lowest energy state. High temperatures are associated with the system being as likely to be in one state than in the other. And we will see it now that we go to the two-level system. I said consider a system of two levels. The difference in energy is epsilon, is the only important parameter that matters in this problem. What is the difference between the two levels? So let me call this level 0 and this level epsilon. The energy of this level is 0 and this is epsilon. You will see later that doesn't matter. I can take my 0 of energy whatever I want. So the system, according to what I said, the partition function, which was the sum over all the states of e to the minus the energy of each state over kT, is very simply the number 1 associated with energy 0 plus the number e to the minus epsilon over kT. That's the partition function of my system. Remember, it's the sum over all possible states of this, and there are two states in my system, so cannot get any simpler than that. So that means that the probability of my system being in the state 0 will be 1 over 1 plus e to the minus epsilon over kT, and the probability of my system being in the state characterized by the energy epsilon is e to the minus epsilon over kT over 1 plus e to the minus epsilon over kT. Because remember, The z was the constant of normalization. If you add this number plus this number, you get 1. So these are the actual probabilities of my system being in one state or in the other. Okay? So there are only two states, so I give you two numbers, now you have the two probabilities.
Where does the P0 equals 1 over 1 plus e to the power of
Is e to the minus the energy of a state over kt. If the energy is 0, e to the 0 is 1. And in this case, it's e to the minus epsilon over kt. Remember, look at the definition. The probability, well, I have to normalize. So the probability in this case is e to the 0, in this case is e to the minus epsilon kt, but divided by these factors, because you check that the sum of these two numbers gives you 1. Why do I want to know that? Because once I know the probability in which a system can be in one state or the other, I can calculate the average of any property of the system I want to calculate. In this case, the first thing I want to calculate is the average value of the energy of my system. Okay? You have a question, Jonathan?
Yeah.
Yes.
I'm very confused with how z is 1 plus e to the minus that epsilon over kt. Didn't we define z last time as the total number of states?
No. Z is the sum over all possible states of the factor e to the minus the energy of the state over kt. That's how we define the partition function. G was the total number of states, then the degeneracy of a state. Now I am not using that. I said you take the factor e to the minus e over epsilon, e to the minus the energy of a state over kt, you sum over every single state of the system, we call that the partition function, which happens to be the normalization constant in the probabilities. That's what I said last time, and I am repeating it now. No connection with the G we were discussing before. Actually, many results you can obtain that way, but we will see that when you want to get entropy out of these things, you can also get entropy and all these things. But this is different. We said there is a factor that Boltzmann introduced, which tells you the likelihood that your system will have a certain energy, because now, in my spectrum of possibilities, my system doesn't have to have only one energy, because it's receiving energy from the environment. So my ensemble now contains many states, but the probability of finding the system in one state or in the other depends on that energy. And depends as e to the minus the energy over kt. That is the whole idea about the Boltzmann factor. Once I finish with this example, I will give you one way in which you can visualize it better. But for the time being, this is mathematics. This number plus this number give you 1. So this is the probability of the system being in the state of energy 0. This is the probability of being in the other one. So if I want, let me do it here. If I want to calculate the average energy, very simple. I have to sum the energy in every single state multiplied by the probability of the system being in that state. Okay, that's by definition the average energy. Since I know the probability of being in one state, I multiply that by the energy. This is by definition, this is mathematics. But in our particular case, means 0 times 1 over 1 plus e to the minus epsilon over kt plus epsilon times e to the minus epsilon over kt over 1 plus e to the minus epsilon over kt. So that means that the average energy of my system is epsilon multiplied by e to the minus epsilon over kt over 1 plus e to the minus epsilon over kt. That's the average energy, which is what I would find if I measure the energy of the system. Okay, because it's an average over the different states in which it can be, each one with its own probability. Okay, so this is in this particular case, for a two-level system. Okay? Let me show you that there is another way to obtain the energy, not only in this case, in a general case, which is the following. Because remember, by definition, the energy is, I write it again, is the sum over all states that the energy of a specific state multiplied by e to the minus the energy of that specific state divided z. Z is the constant of normalization, okay? This is the definition of what the average energy is for any system, not only for this. But this turns out that you can convince yourselves that is the same as, let me use the notation tau instead of kt. I will put the case at the end, tau, because that's the way I define it. So wherever I wrote kt, I mean tau. But remember, it's a parameter, tau, that has energy units. So this, you can actually write it the following way, as tau squared multiplied by the derivative of the logarithm of z respect to tau. And later on, we'll justify this in thermodynamics. But here you can see it. If you do this calculation, you take the ln of z and you derive respect to tau, you get 1 over tau, 1 over z. The derivative of ln z is 1 over z dz d tau. Okay, so I get the tau squared. And when I do dz d tau, z is the sum of e to the minus epsilon over tau over all the states. When I take the derivative of this with respect to tau, what do I get? I get the factor minus epsilon over tau squared, or minus tau squared, so epsilon over tau squared. So the derivative of this with respect to tau is tau squared over z times the sum of epsilon over tau squared e to the minus epsilon over tau. Okay, because when I take the derivative of minus epsilon over tau, I get epsilon over tau squared. So the tau squared cancels the tau squared, and I get precisely that, the sum of epsilon e to the minus epsilon over tau divided z. So this is an alternative definition of the energy. You see, I told you before that when you know the partition function of a system, you can know any property you need from the system. Here we see that if you know z, by taking a derivative with respect to tau, you get the average energy of your system. That's one example. We'll find later examples like that. And you can check. I am not going to do it as an exercise for you, that if you take the z I wrote for the two-level system, you take the logarithm, you take the derivative, you multiply it square, you get exactly this. So you can check it. Here I calculate it by definition, taking the probability of each state, multiplying by the energy. But if you do this calculation, you get the same number. Okay? So far, so good. What does it tell me? The energy of the system, now since I have it, let me look at it, is a function starting already. This is the function, epsilon times this. So let me plot it in terms of the temperature. At very low temperature, this number goes to 0. So I can ignore the denominator, and this number goes to 0. So the total energy goes exponentially to 0. At very high temperature, this number goes to 1, and this number goes to 1 plus 1, 2, so this goes to epsilon over 2. So if you plot this function as a function of t, which is what I wanted to do, you get something like this. Okay? This is the average energy of my system as a function of tau. Okay? It goes to 0 here, it goes here to epsilon over 2. As you see, it corresponds to what I described before. When the temperature is low enough, the system tends to take the energy of the ground state, which is 0. When the temperature is high enough, the system tends to be equally likely between the state of energy 0 and the state of energy epsilon. So we'll have an energy on average epsilon over 2. So this corresponds to what we intuit about the system. Okay? So if instead of doing that, and let me show you, just to show you, I will do the mathematics a little quicker so we don't repeat something which is boring, but here. Imagine that these are my two states. Instead of calling this 0 and epsilon, I want to call it minus epsilon over 2 and epsilon over 2. Okay? Which is equivalent to saying that my 0 of energy will be there. You understand that it's the same system. The fact that I shift my 0 of energy cannot change. But of course now everything changes because the partition function is e to the minus epsilon over 2 over tau plus e to the plus epsilon over 2 tau. Okay? Because it's e to the minus this over tau. And this is twice the cosh of epsilon over 2 tau. The partition function now is quite a different function. Okay? And if I calculate the average energy, exactly doing the same as before, so the average energy will be what? The energy in this state multiplied by the probability of being in that state, which is e to the epsilon over 2 tau divided z, divided the 2 cosh, epsilon over 2 tau, plus the probability in the other state, plus the energy in the other state, multiplied by the probability of that state, which is e to the minus epsilon over 2 tau over 2 cosh. Remember, as usual, the probabilities are e to the minus the energy divided the partition function. So this is the new energy of the new average energy of my system. Which if you calculate, well, 2 cosh appears on the bottom, 2 cosh epsilon over 2 tau. I have a factor minus epsilon over 2 in the front that multiplies e to the epsilon plus e to the minus e to the minus epsilon. Minus because I have a minus, so I get a minus here. I get e to the epsilon minus e to the minus epsilon, which is 2 sinh of epsilon over 2 tau. So the total result is minus epsilon over 2, sinh over cosh is tanh. So that's the average energy of the system. If I plot it, it's not the same as before. It's clear, if I relabel the energy of every state, the average energy will be different. But it will have pretty much the same distribution. This goes when the temperature goes to 0, I have the tanh of infinity, which is 1. Okay, so this goes to minus epsilon over 2 here. When the temperature goes to infinity, I have the tanh of 0. And the tanh of 0 is 0, so the energy goes to 0. So this will go like this. You say shifted because before I had something that went from 0 to epsilon over 2. Now goes from minus epsilon over 2 to 0. But you see, still valid what I said before. In the case of very low temperature, the energy goes to the energy of the fundamental state, which was minus epsilon over 2. In the case of very high temperature, it tends to go to an average between the system spends half the time in each, half of the time with energy minus epsilon over 2, half of the time with energy epsilon over 2, so on average, energy 0. So you see, it's obvious that it had to be like that, because nothing can depend on how I label. If you want to confirm, and that will be the last thing I want to do in this little example, is to calculate the specific heat, which is du dt. Later on, we'll learn that this is at constant, this is called specific heat at constant volume, and the derivative is calculated at constant volume. In this simple example, there is no volume, so there is nothing to derive, it's just du dt. If I take the derivative of the energy with respect to time, that's what you learned in elementary physics, it's called the specific heat. So I can take the energy, the derivative of the expression I obtained before, I take a derivative, and I will get the specific heat, and I did it in both cases. Let me see, did I do it in both cases or only in one? Actually, you get exactly the same no matter which one you start. Well, let me start from the one I have here. So I have to calculate the derivative with respect to time, to temperature of the quantity minus epsilon over 2 tanh of epsilon over 2 kT. I switched from T to tau. Actually, I will go and show you if I want to get how do I fix it. So in the notation without units, CV is du d tau. Here is the u dt. Obviously, the u d tau has no units because u is an energy, tau is an energy. The u dt has units of joules per degree because this is an energy, this is a temperature, which is the unit of the constant K. So you will see that we will get a K in front. If I wanted to do it with respect to tau, I would get no units, but that's a simple detail, doesn't matter. Let me calculate the derivative. Minus epsilon over 2 is a constant, and I have to take the derivative of tanh. I don't expect you to remember all these things, but the derivative of tanh is 1 over cosh squared of epsilon over 2 kT. If you want, just check it or go to your book of whatever, Calc 3, I don't know when they teach you that. And I have to multiply by the derivative of this with respect to t, which will be minus epsilon over 2 kT squared. Okay? The derivative with respect to t epsilon over 2k, and the derivative 1 over t is minus 1 over t squared. Minus and minus is plus, which is good because the specific heat cannot be a negative number. So I get epsilon over 2 kt squared, but I get an extra factor k. The epsilon is squared, the 2 is squared, the t is squared, the k is not squared, so I put an k outside. As I told you, the total unit of the energy has to be this. Wait a minute. The derivative of the cosh square. No, I have to take the derivative with respect to that. No, that's fine. So that's it. And I get cosh square of epsilon over 2 kT. Actually, well, you can leave it as this. If you had done taking the derivative in the previous expression, what you would have gotten, and I leave it to do you as an exercise, instead of using the second one with the levels shifted, the original one, you would have gotten it, you would have gotten K epsilon over KT squared e to the epsilon over KT over epsilon e to the epsilon over KT plus 1 squared. You know, that's what it would appear. And you can massage this expression very easily to get this one. Because this is e to the epsilon over 2kt. Let me do it here. This is, I will need some more space. But what I am doing is I'm massaging this expression to show you that it's the same as this one. So I will get K epsilon over 2kt squared. The cosh will be epsilon to epsilon e to the epsilon over 2kt plus e to the minus epsilon over 2kt over 2 squared. Cosh is e to the something plus e to the minus something over 2. And the 2 cancels the 2. And all you need here is to multiply by e to the epsilon over kt. If I do that, I will put a factor to get k e to the epsilon over kt squared. I multiply by e to the epsilon over kt, which goes inside here as e to the epsilon over 2kt squared. And this will give me, this factor will give me e to the epsilon over kt plus 1 squared. So indeed, you see, the fact that I shifted all the levels changes the average energy. But when I take the derivative, how that changes the temperature cannot depend on my zero. Among other things, because the specific heat is something that I go to the lab and I measure. And what I measure in the lab cannot depend on where I call my zero of energy. So this is indeed the dynamic of a two-level system. And if I have the transparency here, which I hope I do, of these expressions, can you click here? Yeah. Oops. It's open, I assume it's open, yeah. Here I have the two curves that I mentioned. This is the energy. Instead of plotting the energy over epsilon, so that's why it goes to 1/2 instead of going to epsilon over 2. And this is plotted in units of tau over epsilon. But this is the specific heat. You see, it starts as epsilon. If you look at the expression that I obtained, it started, go back one page, it starts as here, so a little lower, here, yeah, go a little lower. So it starts as a quadratic expression in epsilon, because at very low temperatures this is 1 and this is 2, this is a constant. But then after growing there, it becomes, when the temperature becomes very big, when the temperature goes to infinity, I am plotting epsilon as a function of the temperature, right? Yeah. I am plotting as a function of the temperature. When the temperature is very small, this number is dominated by this number. This is e to the something, this is e to the something squared, so this exponentially vanishes. When the temperature is very big, this number goes to 1, this goes to a constant, but then I get the 1 over t squared. So this decays as 1 over t squared. This is quite a funny thing, that the specific heat of a system, we will see when we discuss ideal gases, that the specific heat of a system is something that goes to 0. This behavior, the specific heat tending to 0, is to be expected. In some sense, the third law of thermodynamics tells me that. that when a system gets at very, very low temperature, most of the degrees of freedom do not contribute. What will happen is that most thermodynamic functions will go to zero. So this is something to be expected. This is not, for an ideal gas, this will be something that goes to a very big limit, and this was known since the 18th century. Those of you who took chemistry 1, this is the Dulong-Appetit law that says that all the systems have a specific heat of 3R or something. We will go over that. The fact that in this system it also decays is a funny thing that happens because the spectrum of energy not only has a minimum, like all systems, but also has a maximum. And this is called a Schottky anomaly. This is a sort of funny thing that happens in these systems, and you will see it in some of the problems I will give you, for example, in the case of the spins, which also has that same characteristic, that there is a minimum energy when all the spins point up, and a maximum energy when all the spins point down. So systems that have maximum and minimum energy do funny things when you look at thermodynamics of them. So this is one simple example. But all I wanted to show you is an application of how these things work. We'll come back to all of this. So at some point I will show you how to calculate, starting from the partition function, the entropy of a system, not from the G, whoever was asking me that before, not from the G, from the partition function. How do I get the entropy? We will learn one quantity that is directly related to the partition function that tells you most of the things you want to know about the system, which is called the free energy of a system. It's just the logarithm of the partition function, essentially, or multiplied by the temperature or something. A very simple expression. And once you know the free energy of a system, you can predict what will happen under most circumstances, etc. So we are going to come back to this. So I will leave it for the time being. And I am going to start discussing a little bit, well, before I actually start with kinetic theory, I told you last time that if you look at the book by Blandel, it gives a very funny computer exercise, but gives you a very good feeling of what's behind the Boltzmann factor, and I want to present it to you. You can play with it or show the results. I believe I plotted a few here. And he comes with a completely crazy model. He says, imagine that I have a system 20 by 20. Okay, I'm not going to do 20 by 20, I'm doing enough of this. But you know, these are fixed particles, and each particle can be in a state of energy 0 or 1 or 2 or 3. So each particle has a ground state of energy 0, but can be in a state of energy 1, 2, 3, 4. And we assume that initially you prepare it in any particular state you want. So for example, the initial state he chooses here is a very crazy state, is the Marxist state. You know, he says, let me consider total energy equal to 400. But I will do it in a very Marxist way. You know, we are in the primaries, perhaps Bernie will win, so better get used to that. So he puts 1, 1, 1, 1, 1, 1. So the 400 units of energy, I put them 1 in each box, instead of putting 5 here and 0 here. So I start with the most egalitarian distribution, which, as you agree, it's a very unlikely state. Because if you count how many ways are there to do this, there is only one way to put the 400 ones there, as opposed to any other state. And he said, let me imagine that there is some interaction between these particles. The total energy is conserved, so whatever I do, the total energy has to be 400, but I can assume that somehow a particle can interact with another particle and do the following. Particle I can give 1 unit, let's say this particle interacts with this one, so it gives 1 unit of energy to this one. So each time there is an interaction, particle Ni goes to Ni plus 1, and particle Nj goes to Nj minus 1.
Those lines are energy or particles?
Are particles, but each particle has a certain energy.
So what are the dots?
Pardon?
What are the dots?
No, the dots are the particles, but in each particle I have to put a number telling you how much energy that particle has.
They all have energy one.
Yeah, so initially I pick that state. But what I will do now at random, I will pick one, I will pick another one, and I will transfer a unit of energy from one to the other, and then I'll do it again. Obviously, I have to make a rule what happens if a particle has energy 0. Obviously, it cannot give anything. In that case, I will simply ignore that and try again. So a particle cannot have energy below 0. And I will do that. So you can set it up in the computer and say, pick a cell at random, pick another at random, increase one by one, diminish the other by one, and do it. You agree that this will conserve energy, because one particle decreases the energy by one increases by one, all the others do not change. So if I do it, every single state I generate will have energy equals to 400 in this example. So imagine, after one iteration, I will have 1, 1, 1, 1, 1, 1, 1, but I will have a 0 here, and I don't know, here I will have a 2. Okay? That's all it can happen, that one state now has energy 0 and one has a 2. You see that already this state has much higher probability than what I was before, because how many possible configurations lead to this? Well, I have 400 ways of choosing the particle that goes to 0, and having done that, I have 399 ways of choosing this particle. Or in other words, it's the combinatorial 401 and the combinatorial 399 and 1, which, if I wrote it here, is the number 159,600. So why do I tell you that? Because now you understand that if at random I repeat this again, the chances to going back to picking precisely this and putting a 1 and going to the other are very unlikely, because there are 150,000 ways of doing this, and there is only one way to do what I did before. So if I pick another one, let me do one more, and that I will step. So what can happen? I can pick another number 1 and send it to another number 0. So I will have 396 now particles with energy 1, 2 particles with energy 2, and 2 particles with energy 0, which is still 400. And if you want to count how many ways you have of doing, how many configurations associated with that, well, you have combinatorial 402 for all the ways to choose the 2 particles that will have energy 2, and combinatorial 398 2 for the 2 particles that will have level 0. And so that's the number of states characterized by this distribution of energy. And that number, I did the math here, is 400 times 399 over 2 times 398 times 397 over 2 is around 6,343,000,000. Okay, I just calculated once. 6,304,439. No, not 6 billion, 6 trillion, right? No, 6 billion, yeah. That's one possibility. Of course, if I am in this system, another thing that could happen is just by chance. Instead of picking one of these, I pick this one. And so this one ends up with 3. And this one ends up with, and another one ends up with 0. So another thing that could happen is that I end up with 397 particles now with the 1, 2 with the 0, and 1 with energy 3, so that I pick a 1 and I go there. So where did I get that? I said if I have all 1s, I have a 2 and a 0. And one possibility I calculated before is I pick a 1 here and I send it to here. But another possibility is that I pick the 1 here and I send it to here. That can happen. So I will end up with 397 times the number 1, 1 times the number 0, sorry. If I pick the 1 here and I send it to 2, I will have 2 zeros. No, 2 particles with 0 and 1 particle with 3, correct. And so if I want to count how many ways I have to do that, I will have 400 ways of choosing the place that has the 3, and then I will have 399 combinatorial 2 to choose the ways to pick the zeros, and all the others have 1, and this is 400 times 399 times 398 over 2, or 31 million. So you see, already we see that it's this, although it's much more likely than what I started with, it's much less likely than this. And if I keep doing that, and I do it many times, what will happen? Well, I am not going to do the math, of course, but what you will end up with is something. Now let me show you the picture. Or you click here. This is Boltzmann. No, the next one. No, the next one. Okay. So this was the initial state, all 1s, and this is the distribution. Everybody has the same energy, so 400 of them have energy 1. This is the distribution after, I don't know. Well, this is the distribution after 1 try. 1 of the particles has 2, 1 has 0, and all the others have that. So it's still a very strange distribution, but if I keep going, after enough trials, after I try 50 times, you end up with this. The probability of the state 0, 1, 2, 3, 4, 5, etc. approaches very much the Boltzmann distribution. So the relative probability of having 0 with respect to 1 to respect to 2 is e to the minus 2 over the temperature, etc. Not the temperature, because there is no notion of temperature here, but this will very much imitate e to the minus the energy. This is another example in which he doubles the energy. Instead of 400, instead of starting with all 1s, he started with all 2s. So the total energy is 800. And he ran it, and you see that it gets much closer and closer and closer to the Boltzmann distribution. And if you show the next slide, you will see when he did it, I believe he took 1 million particles. And he ran it, and instead of plotting the bars, he plotted the logarithm. And you see it's a perfectly straight line. So the logarithm of the height of those bars is directly proportional to n, which would represent the energy. Remember, the energy was 1, 2, 3. So this is the logarithm, if you want, of the probability versus is the logarithm of the probability versus n. And since the probability is e to the minus n over something that represents the temperature, we get that the logarithm is a line of slope minus n. So you can generate just by playing, doing this simple algorithm, just pick particles at random and send the energy from one to the other, which is what happens when molecules interact here in this room and they exchange energy with each other, that they will end up having a distribution that reflects exactly e to the minus the energy, which is what Boltzmann insisted. So you see, this idea that systems tend to probabilistic distributions that are e to the minus the energy of the state is essentially you have to assume nothing to obtain it, because there are less assumptions than here. You can just simply say, when each particle gains something, this other particle has to lose. And let me keep doing it forever. At the end of the day, you end up with a distribution that looks very much e to the minus the energy. Of course, in the thermodynamic case, it's e to the minus the energy over kT. In this simple model, there is no temperature, although you can assume that if the total amount of particles I put, the total amount of energy I put initially plays a little bit the role of temperature. But I wanted to show you because it's a beautiful way of seeing that the Boltzmann factor is nothing else than just playing with probabilities. You don't need to assume anything except that particles can exchange energy and the total energy of the system has to remain constant. And this is a good point to stop this discussion, because now, using that, we can start discussing the great contribution of Maxwell together with Boltzmann, which is what we call the Maxwell-Boltzmann distribution, which is nothing else than what is the distribution of the velocities of molecules of a gas. That was a problem that obsessed for a long time Maxwell, although we tend to think of Maxwell as a person who only cared about only cared about electromagnetism, but he cared a lot about properties of gases. And one of the problems he thought very hard, and he proposed the distribution that then Boltzmann justified a little bit, and it's called now the Maxwell-Boltzmann. So that will be our entrance to kinetic theory, discuss that precise problem. What is the distribution, if you want, of the velocities of the molecules of oxygen in this room now? And so what I am trying to develop is the mathematics of that. Later on, when we discuss the thermodynamic of ideal gases, we'll see a little more of a physical justification, but for the time being, we need to understand this distribution, and we need to know how do we know that this is correct, because the first great prediction of kinetic theory is that people measured those distributions and found that it described very well the system. So, what were the assumptions that Maxwell sort of left? He said, there are particles in this room that are moving around. Remember, the notion of atoms was a notion very highly debated in those days. And he said they are kinetic, they have certain kinetic energy. In the case of Boltzmann, that tried to justify this a little better, he was a firm believer in atoms, so he said, well, I assume that there are molecules, each molecule is moving around, has a kinetic energy given by this, and I will assume that the molecules do nothing else. Obviously, if we want to do a theory of the atomic molecules that can rotate, we'll have to do something a little more complicated. Or if we want to assume molecules that can vibrate, there are more degrees of freedom, and we will do that at some point. For the time being, a molecule is a point that only has translational degrees of freedom. This is the energy. Okay? So the energy of a molecule is simply given by that. And we assume we have a bunch of identical molecules, and the assumption that we will have to test later to see if it is really true is that these molecules are flying around and most of the time don't see anyone else. In other words, that the distance between two molecules at any given time is much, much bigger than the size of the molecule. So that most of the time they move freely, they don't interact with each other, but only from time to time they cross paths, they interact, or they hit the wall and they interact with the wall. But most of the time, the only important thing is their kinetic energy because they are free in space. Obviously, this assumes that the intermolecular distance, lambda, is quite big compared to the size of the molecule, and certainly Boltzmann had no way of knowing that. That was one of the basic assumptions. We'll have to check when we get the distribution, and so we know the velocity, we know everything, we will come and check that. That's one of the things we need to check. And he assumed that when they interact elastically, so if one loses energy, the other gains exactly that amount of energy, etc. And he assumed that they are in equilibrium. What does it mean? That each one is in a gigantic thermal bath, a soup made by all the other molecules. So in that sense, we can say that that molecule is in equilibrium with the thermal bath. And that's why we want to apply the idea of the Boltzmann factor we discussed here, because we are assuming that each one moves in the milieu given by all the others. Okay? So, assuming those two things, well, now we want to discuss the distribution of the velocity. So, the first step is a very simple one. What is the probability that if I pick an arbitrary direction, and I call it the x-axis, the x component of the velocity, remember velocity is a vector, that vx will be between the numbers vx and vx plus dvx. So that the velocity in the x component will be here. So I want a distribution that gives me the probability of that happening, which will be, I will call it g of vx dvx.
What's the most left dx?
Well, I say the molecule I am studying has velocities. What is the probability that the velocity lies between an arbitrary number vx and the number vx plus dvx? That's the distribution. That's what you learn in the course in probability, right? In statistics.
Yeah.
I want to calculate this function. I mean, that's what you would do in statistics, the distribution of the velocities.
No, it's not out, so it's like both the middle and the left.
Yeah, well, this is my particle.
Yeah, sorry.
I am saying that my particle lies between Vx, the x component. I want to emphasize that I am saying it for one component, one arbitrary component. You can tell me, are all the components the same? And that's a good question. After all, we tend to assume that in this room there is one direction which is special, which is where the Earth is, and there is gravitational potential energy. So you have the right to assume, well, what I learned for this direction might not apply to this one. Actually, his assumption was all directions are equivalent, that the molecules in this room, if I look at the distribution of velocities in this direction or in that direction or in any direction, I will get the same. That the gravitational potential energy doesn't matter. You understand? It doesn't matter. I mean, there is gravity, obviously. But if the kinetic energy of a molecule is 1,000,000 times bigger than the difference between mg delta x, then it doesn't matter, really. So we will have to verify. Once we know the velocities and the average value, we will have to verify if it is true that I can say gravity doesn't play a role, because he was starting to study the distribution of molecules here. You can say, well, I want to study in space where there is no gravity, but you know, we'll check that. This is remember, that's another thing to check. Once we find the average kinetic energy of a molecule, we want to compare with the gravitational to see if it is true that what I see in the x direction or in the y or in the z will be the same. But for the time being, let's assume that that's the case. So he said, well, very simple. G of the x will be proportional, some constant of proportionality, times e to the minus 1/2 mvx squared over kt. That's the Boltzmann distribution, right? Where this is the energy associated with the x coordinate. Okay? So, and he said, I don't need to know what this constant is. That constant is very easy. I sum for all vx, and this constant has to be whatever I need so that this function is a well-defined thing. So I said, if you integrate from minus infinity to infinity, c e to the minus mvx squared over 2kt dvx, this integral has to give me 1. So this integral gives me 5, this constant will be 1 over 5, and that's it. And luckily, you have a professor who spent the first lecture here teaching you Gaussian integrals. Now you know why we need Gaussian integrals, because we will do, in this class alone, half a dozen of these integrals. So this is, remember, this integral is what we call I0, and is square root of pi over alpha, where alpha is m over 2 kt. M over 2 kt.
You have a factor of 2 there?
Pardon?
You have a factor of 2 because from negative.
1/2 mv squared, that's the kinetic energy.
No, I'm saying about the integral because.
No, from minus, I define the I0 or I2 as the integral from minus infinity to infinity. For the odd ones, I put the factor of 2, not for the even ones. So this integral is what we call I0. So as you see, this integral is then 2 pi m 2 pi kt over m. Is that correct? Square root of 2 pi kt over m. That's the integral, which means that the constant of normalization, now I know g of vx will be the function square root of m over 2 pi kt e to the minus m vx squared over 2 kt. So if I happen to be able to measure the x component of the velocities of all the molecules in this room, assuming they have mass m and the room is at temperature T, I would get that the probability of measuring one that has velocity Vx is given by this mathematical expression. That's the simplest case. But already knowing this, we can calculate a few useful things. Let me point a couple that we can. For some, we'll need to go to a three-dimensional case. One first thing, what is the average x component of the velocity of a molecule? If this is the distribution, it's simply square root of m over 2 pi kt times Vx e to the minus m Vx squared over 2 kt. Between minus infinity and infinity. That's by definition the average of Vx. Okay, I multiply the Vx. I don't have to tell you that this integral gives you 0. Okay, because this is an even factor, this is Vx, so this integral in minus 3 is minus the value in 3 and so on. And this is nothing else than telling you that if you average all the velocities of all the molecules in this room, there will be as many moving to the right that you will find to the left. But there is nothing special. So we could have guessed that, but it's good that we get it. More interesting, for example, are two quantities that we can calculate. One is this. The magnitude of the x, okay, averaging that. That obviously will not be 0 because now we are averaging all positive numbers. So what is the average speed in the x direction, or the x component of the speed? And that is an integral that we can calculate. Now, well, you can do this. From minus infinity to 0, I have to put minus Vx, right? Vx e to the blah, blah, blah. And from 0 to infinity, I have to put Vx e to the blah, blah, blah. Why? Because when Vx is negative, the magnitude is minus Vx. And so let me massage this a little bit. The minus, I can use it to change this integral from 0 to minus infinity. I reverse the limits of integration. And now I want to change Vx by minus Vx. If I do that, minus Vx, I will call it, if you want, V prime x. So here I will have a minus V prime x. And here the exponential, nothing changes because I have Vx squared, but I have here the dVx, right? So this minus, I will use it to change the differential. So I'll get now this integral like this. The integral of V prime x e to the minus 1/2 m V prime x squared over kt dV prime x. The only thing is that since I changed x by minus x, this integral doesn't go from 0 to minus infinity, it goes from 0 to plus infinity. And so this integral becomes identical to this one, so I can take this one and put a factor 2. So it's 2 times the integral now from 0 to infinity of Vx e to the minus m Vx squared over 2kt. So now you see, this is the integral that will give me the average magnitude of Vx. It's twice, but now the integral from 0 to infinity. Now it doesn't vanish. This is what we call I1. Remember, the integral Vx times e to the minus something Vx squared is the Gaussian integral I1 with that factor 2 included. So let me do it. And so that will be exactly, where did I get it? Here. I have to put 2, the square root of m over 2 pi kt. And I have to put, and now is the I1. And the I1 was 1 over alpha, was that integral, right? Divided, including the factor 2 was 1 over alpha. So 1 over alpha is 1 over, sorry, m over 2 pi kt, and 1 over alpha. 1 over alpha is m over 2 kt. 1 over alpha is 2 kt over alpha. So when I combine those two things, I get what? Kt over m appears in the square root, and I get the 2, and I get the pi on the bottom. Nobody cancels that pi, so I get the square root of 2 kt over m pi. So that's the average Vx. I don't know why I wanted to calculate that, it's not that useful. The more useful is this quantity, the average quadratic velocity, because that allows me, the square root of that is what we call the RMS velocity. And that is something that we need to know because we will use it, you will see very soon, for a bunch of things. So that is square root of m over 2 pi kt. I will box all the results together in a second. Times the integral of Vx squared e to the minus m Vx squared over 2 kt from minus infinity to infinity. So, and this quantity is what we call I2, which, if you remember, was square root of pi, 1/2 of square root of pi over alpha cubed. So let me get that, because that I need. M over 2 pi kt, 1/2, which is important, and I get the square root of pi over m over 2 kt to the power 3. That's important. That's 2 kt over m to the power 3/2, and here I have 2 kt over m to the power minus 1/2. So all together I get 2 kt over m. The square root of pi and the square root of pi cancel, and this 1/2 cancels these two, and I get kt over m. And that's correct. Yeah, absolutely. That has to be like that. So, by the way, let me point this result that if you calculate the average value of 1/2 mvx squared, it's just multiplying what I just got by m and dividing by 2, it gives me 1/2 kT. Here you have the first glimpse of something that is one of the fundamental theorems of statistical physics, that tells you that if you average any particular term that appears in the energy, you will get 1/2 kT. So that's it. We will discuss that. That's called the equipartition theorem. And we will discuss it at the end of the class today. We will discuss it, or perhaps at the beginning of next class. But that's very deep. That says that when you have a system that all the particles interact with each other, every degree of freedom gets on average an amount of energy 1/2 kT. So that's another interpretation of what temperature means in statistical physics. Temperature sets the scale of the average degree of the energy. In this case, this one.
T is temperature, right?
T is the temperature, yes,
KT.
absolutely. And
Transform.
kT is an energy.
So the new definition of temperature is just a scalar of...
Yeah, we will show that when you have a system that has n degree of freedom, if it is in statistical equilibrium and the system has in its energy n quadratic terms, you will get n over 2 kT. But we will come to that. For the time being, just reflect that if I average this, I get this. By the way, to summarize all this discussion, what did I find? I found that the average Vx is 0, which I knew. If I calculate this, which is what we call the root mean square velocity, I get square root of kT over m, because Vx squared was kT over m. And if I calculate the average value of this, of the magnitude of this, I got square root of kT over m 2 over pi, if you check what I just got. So this number is bigger than this one, because 2 over pi is 0.7 or something. So if you calculate, instead of calculating the average value of the x component of the velocity, of the magnitude, you get a smaller number than if you calculate the root mean square value of the x component of the velocity. And I will say one more thing and then we'll stop. I'll say that now, why did I do all this work? Because now that we did this, we can address one of the problems that Boltzmann thought about, which is, if I look at all the molecules in this room, what is the actual distribution of the velocity? So I want the function f of Vx, Vy, Vz, dVx, dVy, dVz, that tells me what is the probability that if I pick a molecule, the molecule will have a velocity will have a velocity such that the x component lies between the number Vx and the number Vx plus dVx. The y component lies between the number Vy and Vy plus dVy, etc. Okay? This is what I would call knowing the distribution of all the velocities, not just one component. Okay? But all the work is already done in some essence here, because Boltzmann assumed the simplest possible idea. He said, all these velocities are independent. If you tell me that the x component of velocity is 37 meters per second going that way, you are giving me no information about if the y is in that direction or in that direction. They are all independent. So he said, this function is just g of Vx times g of Vy times g of Vz, because they are totally independent. And of course, g of Vx is what we just calculated, and g of Vy will be exactly identical, and g of Vz will be exactly identical, because we said that nothing depends on which particular direction I pick. So what you will get is that you will get square root of m over 2 pi kt to the power 3 now, this is the new exponent, e to the minus m over 2 kt vx squared plus vy squared plus vz squared. Because I have the exponential of vx squared multiplied by the exponential of vy squared multiplied by the exponential of vz squared, and sum the exponent. And this obviously is nothing else than e to the minus 1/2 mv squared over kt, where v is the speed of the molecule. Okay, so this gives me the distribution of the velocities of the molecules. And as you see, they depend absolutely not only, the only thing that matters is the speed of the molecule, because if Vx is bigger and Vy is smaller, and this doesn't matter, because all it appears here is the magnitude of the velocity square, or the speed square. So this function, f of Vx, Vy, Vz, is this factor I just wrote here, m over 2 pi kt to the 3/2 multiplied by this. This is still not what people call the Maxwell-Boltzmann distribution, because this is the actual distribution of the velocities, as it says here.
Where does the 3 has come from?
Sorry, 3. If I put 3/2, I don't need the square. No, sorry. That's the expression. We are almost there. Why are we not there yet? Because what Boltzmann was after and what he calculated is not the distribution of the velocities. He wanted a function f of v dv. What is the probability that the speed of the molecule lies between the values v and v plus dv, which is not the same as this. This tells you what is the probability that the velocity of the molecule has specific coordinates, Vx, Vy, and Vz. Okay, what he wanted is something much simpler. I want to know what fraction of my molecules have speed of 50 meters per second, how many have 51, and that's a simple calculation based on this, which we will do. Requires a couple of steps, but not that many. Requires 2 steps. But we will do it after the break. And then we will have the actual Maxwell distribution of velocities. We can calculate its properties and see what are the basis of its experimental verification. So let me stop here. But remember, this is just an intermediate result to get the distribution of the speeds, which is what was of interest to Boltzmann and to everybody, because that's what we can measure actually in the lab. Okay, I am stopping here, and we will resume 10 minutes.